You might recognize me. I've been on a few of these calls now, but my name is Shane Jenkins. I'm a project manager with HeroX, and I'm going to be moderating today's call. I have the pleasure of having watched these teams here compete over the course of this competition and submit their fascinating solutions that the judges eventually chose as winners. And we have the chance today to actually hear them tell us about their stories and show us how they came to the solutions that they did choose. Additionally, we have a representative from NASA, Andy, we'll get to in a moment. He's going to tell us about the challenge's backstory. But first, why don't I pass it over to Jeff here to give an introduction for himself?
Okay. Are you going to show those slides yet, or is that going to be later?
That'll be later. Let's just do a quick intro for all of
Okay.
you guys.
Okay. I was the captain on this. My name is Jeff Morris. Our team is named Team Widget Blender. My background is an aerospace degree from MIT and a MBA from George Mason University. And I'm in the Northern Virginia area, and we also have I have two other members on the team. One is a Dr. Steve Wu, and he has a PhD in chemistry, and he lives over in Taiwan. And then our third, why don't you introduce yourself?
Go for it, Prax.
Yeah. Hello, everybody. Myself, Prax, and you can call me Prakriti. So I'm basically from Mandya. Currently, I'm pursuing third year of Electronics and Communication in Alvas Institute of Engineering and Technology. And yeah, I'm from Team Widget Blender.
Wonderful, thank you. And Dimitri, can I pass it to you?
Hello, everyone. My name is Dmitry Gerin. I'm a structural engineer based in New York City. I'm also an aerospace enthusiast, and I found this challenge topic interesting to me and important to the world, so I thought I could come up with a good solution. So I'm excited to share my idea today.
Oopsies, wonderful, thank you. And it looks like Craig himself might be having some challenges with his microphone. So if you want to put your introduction into the chat, Craig, you're welcome to until we get that sorted out. But I'll happily bring it back to you if you're able to get that sorted. In the meantime, though, Andy from NASA, can I pass it to you for a quick intro?
Oh,
yes.
No. Yeah.
Yeah, I'm not cut off, but I'm going to turn on my video for the intro at least. Yeah, I'm Andy Provenza. I'm the Deputy Project Manager of Technology for University Innovation and the prime author of this challenge. In my two-chart presentation, I'll talk about why we created this challenge, what we were potentially looking for, and why. My focus inside of University Innovation is to manage the zero emissions aviation portfolio, which we hope to grow someday. It's a part of one of our pillar projects inside of aeronautics, looking at alternatives to Jet A combustion for aircraft, and also even looking beyond SAF, which is the current train of thought where we would take advantage of the carbon offset if we create SAF, hydrocarbon fuel, with carbon dioxide that either is absorbed by plants and we use those plants to create that fuel, or we actually capture it to create fuel through some other processes. So I will stop there, Shane, and maybe we can get Craig on.
That's great. Yeah. Any luck there, Craig? Feel free to message us in the forum, or I see. It sounds like you're having some Windows issues. If you are able to quit and rejoin, though, Craig, you're very welcome to. You should be able to hop right back into the webinar if you'd like to, and then we'll be able to give you the mic. Or if you want to join from another device like an iPhone or something, we can give you the microphone when needed, so that you're able to present. One more note, though, before I pass it to Andy for his two slides. I just want to give a quick shout out to those who aren't on the call today, but who played a major role in this challenge. I want to give a shout out to our judges' choices, Baha Abunaga and Douglas Thorpe, for their entries, as well as Team Solar Powered Aviation for their honorable mention performance. They also did a wonderful job participating in this challenge, along with our many other talented competitors that will be able to join us today. And then additionally, I think in our chat, we have two of the people who helped design this challenge, Douglas Clark, Jamie Elliott. I want to give a shout out to them for their great work in bringing this opportunity to the public. Alrighty, it sounds like Craig's just going to leave it be. He's not able to work something else out. So with that, Andy, how about I pass it to you for your presentation?
Okay, let me see if I can do a screen share here. I'm going to share my screen too, and then bring up okay. Can you see anything on my
looks like
screen too?
Looks like it's just loading there. Now we can.
Okay, you see a table?
Yep.
And it's not in presentation mode. I'm going to put it in presentation mode. And can you see it in presentation mode now, Shane?
All good. Yep.
Okay, great. So I put this chart up first because inside of University of Innovation, where I manage a portfolio, we fund projects inside of NASA Aeronautics. Now, NASA Aeronautics covers what we call thrusts, and there are 6 strategic thrusts. If we start over on the left-hand side, the first column there, we look at air traffic operations in thrust 1. We look at high-speed flight, civil, commercial, supersonic transport. There, we also look at in thrust 3 subsonic transport, so kind of where this project falls into. Thrust 4 is vertical lift, so we're now looking a lot at vertical lifts. You're seeing a lot of activity in that area. We look at manufacturing and materials and structures. Sometimes we fund things in those areas. Thrust 5 is system-wide safety, so looking at growth of global operations and how can we maintain safety when we include things like reusable vertical lift vehicles and that technology. And then autonomy. Autonomy is a big activity now, and that's falls into thrust 6. And we have once in the past looked at hypersonics as well. So a lot of columns that we look for proposals within this University Leadership Initiative effort. It's a yearly proposal process. We fund typically 4 awards. They're multi-year efforts, 4-year efforts at up to $2 million a year. So pretty good funding for a university community. Who proposes to this? Well, this is university innovation. So universities team up with other universities and industrial partners, and they propose their own ideas to address these thrusts or these challenges inside of NASA Aeronautics. So if we take a look at the third column, which is doubled up there, the right side of that, those are projects that we are currently funding inside of zero emissions aviation. So these are projects that look at liquid hydrogen as an energy carrier for propulsion, whether it be burned in a gas turbine or whether used in a fuel cell or both. Also looking at ammonia. So ammonia has no carbon in it, right? So it's appealing from the fact that it doesn't produce carbon dioxide, which is a major contributor to global warming, as we're pretty certain about. So those 4 projects listed there are our current portfolio. The first one on the left of that column, Ohio State, they looked at electrified hybridization of regional jets and showed a benefit there. Developed a motor, but it was a project that gets grandfathered into zero emissions aviation portfolio of ours, but it's closed out. So, I mentioned ammonia, hydrogen, there's hybrid electric. People have looked at blended wing bodies, modified tube and wing. The Cheetah project, University of Illinois, has hydrogen tanks up top. But what you don't see here, and you don't hear me talk about, are other ideas. And as we've moved forward year after year with inside of this project, we've been really looking for newer, more outside the box ideas. And we haven't been getting those types of proposals. So what we wanted to do was to develop a new portfolio item, a new solicitation looking at wild and wacky ideas, we were going to call it, or ideas sort of outside the box, things like laser power or solar power beaming from the earth, or nuclear propulsion, or burning metal fuels, just to throw out a couple of examples of things that we haven't seen. So we wanted to try to attract new ideas there, but we didn't have the funding to do that. But what we did have funding to do was to hold this competition, to expand our net, to cast it out farther than just the universities inside the US, and see what we get. Could we get any ideas that are outside the box that look promising, and then maybe potentially work on those? So obviously one of the questions that winning teams would have is say, hey, when can I get NASA money to work on this stuff? Well, we currently don't have any funding for that, but as is mentioned in the solicitation for this competition, any future work would have to involve universities, at least with us, because we work with universities. That's our prime goal, is to develop the next generation workforce working on these types of things, working on NASA challenges. So it could be that they find their way in these ideas into somewhere else. We will be having some follow-up meetings, taking a look at some of these top ideas that you have, and what could we do with these. However, one thing that you could do on your own, and I can provide you with some contacts for each of the top 3 winners here. Can you team get your idea out with somebody in university and be a part of a team that proposes to this university leadership initiative and eventually win an award inside of that third column? Okay, so that's where it could potentially go. Ideas could go within my respective area. Last slide I wanted to show is this. This is a popular chart that you see everywhere. In fact, a lot of people showed this at SciTech, AIAA conference. And if you focus in on the top, contrails and CO2 are big contributors. Red is bad. So anything going to the right is bad on global warming, let's say. So if you take a look at that first bar, you see these other bars, these black bounding bars, which is at least in 2021, the uncertainty associated what the true negative impact is of contrails on the environment. Well, heck, if you're at that left side bar, maybe contrails aren't really that bad. And in fact, contrails during the day are actually good. It's the ones at night that are problematic. So those are ones that we really should be addressing. If we take a look at carbon dioxide, the next bar down, at this stage in 2021, it looked like it was a little less potentially harmful, maybe on average with their level of understanding. The error bars are much tighter there. So yeah, carbon dioxide does look like it's a problem. That was something that we were looking to address primarily in this challenge. If we jump all the way down to net for NOx emissions, so towards the middle, just above the middle of the chart, you see a smaller red bar with error bars that go all the way to 0 for NOx. So is NOx bad or is it good for flights, say, in the troposphere where most of our air transportation takes place? And then there's water vapor, and there's some other things, but I just wanted to focus on those 3 bars, and those are the types of things that we're looking to address in this challenge. Can we make those bars go away? And some of your ideas certainly suggest that there is a possibility if we look at some of these ideas. Okay, that probably took much more time than I wanted it to, but I'm going to stop sharing. That's all I had. I had lots of other stuff that I could show, but I did show it during the webinar, which I believe was recorded, Shane, and people could take a look back at that. Good.
That's correct.
Hey,
Yes.
The screen was covered by the secondary PowerPoint. I'm like, uh-oh, have I been talking this whole time to nobody?
No, you did a great job. Thanks for that,
All right.
Andy.
You're
And that's
welcome.
true. I will say, if people want to go to herox.com/pureblueskies, you can find that past webinar in the updates tab where Andy did give a more in-depth presentation. But thank you for that, Andy. It's really helpful. The one thing I'll say that I'm really curious about is if anyone from other universities is watching this and just following along, like you said, any further work that comes from this wider net we've cast would have to be done through that process or through those vehicles. And so I'd be really curious to see if any other university representatives are watching this, which of these upcoming solutions sticks out to you? Is there anything that you feel is particularly suited to your capabilities or your school's resources? So keep an eye out. With that said, though, I'll just give a quick reminder to people before we start sharing each of our individual teams' solutions. If you want to put any questions into the Q&A chat at the bottom, we'll be able to answer those towards the end of the call. I see you've also had Kevin Kempton join us, who's from the COSI team at NASA. I just want to give you a quick welcome, Kevin. Thanks for joining.
Hey, everybody. Like I said, congratulations on winning. What that shows is that your ideas are credible, and you had a panel of, subject matter experts look through your ideas and say, hey, there's something to this that might be, something we can use in the future. Right now, I work with COSI, which is in the Space Technology Mission Directorate, and Andy is from, I think you're from the Aeronautics Mission Directorate, and there's also the Science Mission Directorate. But on Space Technology Mission Directorate, it's broken out into early stage and mid range, and then technology demonstration. So we're fit solidly into this early stage stuff. So we look at stuff it's typically a fairly long way out, and you got to fund this kind of stuff because you've got to have this set of ideas that can move forward, that people can look at and let it percolate and slowly increase the fidelity on these ideas, so that when we need it, these ideas have been looked at. And so one of the things we have on our prizes and challenges, we put out challenges all the time. And the nice thing about that, there's some international folks on here. Some of these things we can get ideas from the international folks. Normally NASA, we try to stay within the U.S. because it's funded by U.S. taxpayers. But on a lot of these early stage ideas and stuff like that, we love to get ideas from the international community and give recognition to them, because the amount of people that we have actually working in NASA is very, very limited, and there's so many good ideas all around the world, and we want to try to capture that, and then, if it's possible, move forward. At early stage, we have programs like the NASA Advanced Innovative Concepts, and they're looking for things in the 2050 time range. Some ideas that are not high fidelity and a lot of theoretical work, but you got to start somewhere. And I think Andy and his company did a great job formulating a challenge on a real important issue, and hopefully you guys have stepped up and tried to solve that really important issue down the road, because it's got to be solved. We cannot continue to burn hydrocarbons at the rate we're doing, at the accelerated we're doing, and it's affecting the atmosphere. The contrails are causing a lot of issues. You see it more and more every year, and so anything we can do to start getting these ideas out there and implemented is going to be a big start. So I have to applaud everybody for taking their time and doing it. And maybe, like I said, now that you've got your ideas have been shown to be credible by a panel of subject matter experts, maybe you can publish them and take that recommendation forward and say, hey, this has been looked at. Maybe I can publish my work and get white papers and go to a conference and talk about it. You'll have some confidence to carry it forward. So
I love that. Thanks, Kevin. Yeah, while I get this presentation brought up for you guys to tell us about these long discussed concepts, I guess I'll just add that that's one of the greatest pleasures of working on this competition, is knowing the potential impact it could have. I want to give you all a kudos for looking so far ahead and being willing to trust crowdsourcing in the long term. That often is how things work best when we spread that wide net. That's where crowdsourcing really gets to shine. And so Yeah, I'm excited to share these solutions with you all. So here we are. Can you all see this presentation screen correctly? Good, a little bit of a nod there. Um, let's try to get to advance the slide then. That's step 2. All right, we're going to start off our Meet the Winners portion of the call with Dimitri Garin. Dimitri, if you'd like to take off yourself off mute, I'll pass it to you for your first slide.
All right. Yeah. Hi, everyone. I'm Dmitry Garin, structural engineer based in New York City, and I would like to share, to present my solution for the challenge today. The next slide, please. So, yeah, this one. I would like to present a two-stage aircraft solution consisting of the second stage glider as a blended wing body aircraft, which carries passengers and other payload. And the third stage booster is an unmanned vertical takeoff and landing aircraft equipped with high thrust engines and fuel tanks. Staging is common in spacecraft design when high-performance engines and large fuel tanks are required to launch a spacecraft and then jettison stages after reaching certain altitude and velocity. And a typical airplane flight profile also has high thrust and fuel consumption during takeoff and climb. So after reaching the cruise altitude, the high-performance engines and additional tanks placed on the booster stage get jettisoned similar to how the space shuttle jettisoned its boosters. Also, staging in zero-emission aviation can solve various aircraft and propulsion design problems, such as large hydrogen tanks on board, which increase the body volume and the wingspan, and a large number of electric turbofan engines required to generate high takeoff thrust. The next slide, please. When it comes to stage design, each of the stages represent an independent aircraft capable of takeoff, flight within a certain range, and landing. And together they function as an aircraft system capable of carrying passengers or other payloads comparable to modern mid-range airliners. The glider's blended wing body design is chosen for its ability to fly longer while consuming less fuel. And the booster serves as a reusable VTOL stage. After stage separation, it returns to the airport of origin, gets refueled, and is ready for the next flight. Another distinctive feature of a two-stage system is that the future zero-emission technologies, such as new power sources or aircraft designs for each stage, can be implemented separately without significant redesign of the entire system.
Wonderful. Thank you for that, Dimitri. Again, I'll invite anyone who has questions about Dimitri's innovative solution to put them in the Q&A box, and we'll come back to them. Next up, though, we have Craig, and I believe Craig was having some issues with some of his microphone. So let's see here. He's given me some notes that I might be able to read for you. So as a quick bio for Craig, he's a retired worker from the IT world. He has done some work with Bell Labs, but also work in aviation. He's also a mechanic and commercial pilot, and so in some ways he's nicely suited to this challenge. He has won some past awards, which you can see here, many of them being prior NASA or aviation-related challenges. And so he's definitely a familiar face in the HeroX community. Now, let's see here for your second slide. I'll leave you to read through some of these bullet points here on what Craig's vision was for his solution. But as far as I can understand it, in short, it was a liquid fluoride thorium reactor, something similar to instead of a typical combustion engine, something that is reactor based, although lightweight, as he notes here, compared to uranium. I believe this is something that had been explored in the past, actually, but Craig brought a new angle to it and tried to find different ways to make this prior conceived technology perhaps more feasible for today's day and age. Some notes that he's given me here include, let's see, that the reactors cannot be throttled quickly, that the batteries would regulate the power settings for about 45 minutes. Let's see here. I'm actually going to post these into the chat since Craig's given them to me, since there's actually a bit more info here than I can convey, but that would be helpful for you all so you could read through it. So let's see. Okay, here's what Craig has mentioned about this slide here. He also mentions that the ample amount of power from this solution allows motor generators in the wheel trucks to allow its own engine off taxi, parking, and self push out with minimal ramp equipment. That because it's a different type of reactor, in his description, it's not really bomb material, but rather a full enrichment, reactor enrichment. I guess, yeah, ideally the goal with this one would be to make sure that it is entirely safe. And as Craig has put it here, he believes that this version of technology can be safer than prior versions or other understandings of reactor. I won't say more because I'm afraid that I'm going to get it wrong or perhaps say something that's not accurate. But here is another vision or another view of what Craig had mocked up for his submission and how it will be mounted on the side of the wing here. And furthermore, some other images that he's given to support his solution. So Andy, forgive me, I've only been able to work off of what Craig had offered me in the notes and what I recall from before. But is there any other insight you can possibly give to this solution if you recall it?
Yeah, what we particularly liked about the solution is that it is primarily an electrically powered, battery-powered aircraft. However, there'd be small nuclear reactors that only provided a small amount of power, energy, that would ultimately be there to either provide assist at cruise or and also to charge the batteries, so you can extend the range. So as opposed to trying to use nuclear energy to power the entire aircraft. So you'd need, 30 megawatts to get off the ground. So you're talking about these reactors that are much larger than what Craig proposed here. And it's an interesting aspect where this is almost like it's kind of like what in our area we call range extenders. So possibly the back of aircraft, you'd have an all electric, but then you'd have this engine in the back that was burning fuel and charging the batteries. This is something that the fuel is in the palm of his hand right there, literally. So we've seen some nuclear ideas. This one's different in the fact that it was a smaller amount of energy and primarily a battery-powered, motor-driven propulsor aircraft. Yeah, so very exciting.
That's super helpful. Thank you, Andy. I know that Craig has a few more notes he might share in the chat just to add some context, and so I'll let him do that. But I believe he has one more slide here. Anything else you want me to add for this one, Craig? It looks like he's given some examples of potential use for this technology and ways that it can be deployed for particular issues, such as putting up a communications platform into the air for a prolonged period of time in case of like responding to disaster zones. Okay, oopsies, that wasn't meant to fly that fast. Finally, let's pass it on to Team Widget Blender led by Jeffrey Morse. Jeff, take it away.
Okay, thank you. Okay, this is when you said blue sky, we said, yep, these are gonna be perhaps a bit crazy, but that's what I think you guys were calling for. It's we're a team of 3 people, myself, Dr. Wu, and Prax from India. She's a student.
Yeah.
Check me to the next slide.
Yeah, and in this project, Dr. Wu did a lot of the sort of the more energy and chemistry-based stuff. I focused more on sort of the satellite elements of it and some of the aerospace notions. So we can probably move on to the So here's a little overview of something. Yep. On this little graphic, we have solar power because this is going to be a hybrid hydrogen to take off and land, and in case of emergencies that you lose your solar powered ramjet for some reason. The other slide up there is a little thing where it shows a large MEO, mid-Earth orbit constellation of power stations, which are beaming to our, as in the bottom thing, a cluster of laser beams probably into a laser receiver that is on a blended wing body type aircraft. So we can go to the complex slide. It's the next one. Okay, so let's start up here at the top right-hand corner. The MEO constellation there, right there would be about, we've been using 1,000 satellites as a reference to a mature system, simply because you need to have a number of satellites to replace. Since all satellites are in motion, one eventually is beaming power to an aircraft, and then it moves out of range, and then the other one needs to replace it. And you need a fair number to support a lot of aircraft. So right there is about 1,000. If you can see the slight red dots on the left side of that, that is where the sun is blocked. The sun is blocked, and you can't use that power station. So you need to use power stations that are in the sun. In general, calculations show that only 5 to 7% of the power stations are blocked at any time. A power station in this case is going to be a fairly large thing. We expect it to be over 100 tons. The dimensions will be over 100 meters for a pair of solar cells, giving solar arrays, given current technology and the direction it's going. We also expect perhaps to augment it with a couple very lightweight reflectors made out of mylar to redirect some of the energy to increase the net the net flux on the cells. As you can see here, we have, I think that pretty much, and it's kind of interesting with Dimitri talking about the blended wing body and the hydrogen engines. It's yes, we also SLEP really can only work dependably at very high altitudes for a number of reasons. But essentially, we need some hydrogen engines to take off and land and perform emergency type maneuvers if that came up. But on top, we need a large area, maybe about 5 meters across, and to have we'll call a positive meniscus lens, which one of the challenges, we go down and take a look at the middle left here, is that we have this normal vector, and when we're up there cruising, we're having these what we call them star power stations. They are directing energy at the top of the aircraft. Now, to get in to have it redirected all the way down to the engine, it needs to be within about 20, maybe 25 degrees of that normal. I mean, it might work at 30, but we're trying to say, yeah, it works best when it's directly overhead, but 25 degrees we think will work. I've done some calculations that shows that if you have 1,000 satellites in a 60-degree inclination type 20,000 kilometer radius orbit, that you can usually expect 50 satellites to be able to get within 20 degrees, sometimes 70, sometimes 10. The closer you get to Earth's shadow, the less the number is, but there always is a number down there. And then at the bottom here, I have this little notion of trying to remind you that the laser ramjet engine, which actually did get a patent, and there's an old patent that talks about that. It's about 20 years old, so it's no longer in protection. But we did find something referencing that. So the challenge here is that we're going to be we're shining a beam of light, a beam of laser energy that will essentially get redirected down through this, the purple, what we call that the lens, and then there's a bit of a reflective tunnel. And then at the bottom, we see that we have the red, what we have here is the red engine. And the engine's going to have to be on the bottom because it's going to need to be, for the shape of it. So that's when we go back and we think about these blended wing engines with hydrogen engines as a pair on the back. That works well with this concept. Okay, we can probably move on to the next slide because I want to say, people say, geez, was that 1,000 satellites you need? 1,000 100-ton power stations? That sounds expensive. And it's not cheap, but it's not crazy expensive in our opinion. Right now, aviation fuel is about $6 a gallon. If by 2050 gets $10 a gallon, and if each of these star power stations is 50% utilized on average, then you can save about $50 million of jet fuel every year for every power station. If the aircraft are out there to do the receiving. So if we also go on and say, okay, this whole thing requires Starship, SpaceX's Starship needs to work cost effectively to make this work. These are big stations, but Starship itself is, it is in testing. We have 15 years or 10, 15 years to get that. And this is, I think I'm being fairly conservative. Elon has talked about less pricey launches than 50 million, but I'm just saying, let's say just 50 million. Okay. And if one of these power stations lasts 10 years, then the break-even price of a power station for just supporting aviation is $450 million. And I believe you can make a power station by then that will be less than $450 million. But it gives you a cost point. Another thing about paying for the SPS constellation is that you can also use it to accelerate spacecraft. You can use it to light up lunar night, the lunar night at bases on the moon to give that, to provide energy to them. And, there may be a number of flexible things because, there's times in which, especially like if you're over near the Antarctic, over the Pacific, there's not a lot of air traffic there. So you have an opportunity to use SPS to do other things as well. And then finally, I said here, if we have 1,000, assuming 300 million total, you could save 50 billion in fuel per year if the amortized cost of a star power station is 30 billion. Overall, you get a $20 billion a year annual savings. So we just make the argument that yes, it's expensive, and yes, we need R&D, but the potential $10 billion R&D program for the SLEP blended wing aircraft, and maybe another $5 billion for the power station R&D. It seems like it would not be a budget buster for this concept deployed over 10 years. So the bottom line is we think it not only is very good for long duration flights, like you could keep going in theory for 10 hours, 12 hours, 24 hours, 48 hours. There's all sorts of potential military things that could go with that. But for commercial aviation, I think it's pretty much moving across the planet fairly quickly. And I think we're talking about a 0.9 Mach 9 aircraft that could operate around about 14 kilometers high, which also reduces contrails. So for these long range cruises, we get rid of the CO2. I think we get rid of the nitrous oxides issue as well. And we also potentially reduce the contrail issue. So that's kind of my pitch of crazy idea, but the economics could work with the right investment. Oh, by the way, and one moment here. One of the things that there's a few real tech challenges in these boxes, and one of them, of course, I assume you're thinking that laser is a real tech challenge, and perhaps was looking into our laser issues. And would you like to say anything about this?
Yeah. Actually, lasers, we have used fiber lasers, like it could also convert the solar energy into laser light. So which is already like beamed into the distance spacecraft or satellite and converted back into the another solar energy. Like it could also provide continuous power supply for the long duration of the spacecraft, along with for the other application is for the satellites and shadowed regions also.
Thank you.
Yeah.
Wonderful. Thanks, Paul, for sharing your solutions here. I hope those of you in the audience really enjoyed hearing about these. These are only some of the many amazing ones we got, but they are also our winners. So they definitely rose to the top of the crowd here to deliver these solutions to us. Okay, I think I've stopped my screen share there. Let me just check if we've got any questions in the Q&A box. But before I pull any up, I'll just say, Andy, anything you want to say in response to the three winners? Oh, sorry, you're muted. My bad.
No, I have control. It's my fault. For me personally, it's really nice to put faces with the names on these award winners. I really also enjoyed hearing your descriptions of your ideas. You know, I see a lot more has gone into SLEP than really you proposed. You've done a lot more further analysis on that, which I find really fascinating. You know, each of these is really quite different. You know, the two-stage concept that Dimitri has is really intriguing, and you know, we've kind of talked about that internal a little bit. Find it quite interesting. I did mention in my intro that that I think that I can provide points of contacts at universities for each of the three projects. So I would just do that via email with you. So if I can get email addresses, Shane, and can do a follow up on the things that I mentioned there. Yeah, lots of challenges associated with all three of these that certainly I would think some of you in the audience there could think of, and possibly dangers, right? Nuclear fuel on an aircraft. You know, how well does that first stage booster fly at Mach 0.78 when it separates? Boy, space lasers. What are other countries?
Laser. Yeah. Right.
With space-based lasers, what are other countries going to think if we start putting lasers up in space that actually have enough power to power an aircraft?
Yeah.
So yeah, just a few things that I can think of. Yeah, but really great stuff. And you know, I'll say personally, Shane mentioned how fun it was. We had a really good team putting this together as we came up with the narrative, made it fun for this, and I really enjoyed the process. And it culminates with this ceremonious webinar, if you will, and really excited. And I hope you guys are happy that I'm sure you're happy that you won. Got a little monetary award and things. So congratulations one last time.
Thanks. Thank you.
Thank you.
Thank you.
Well put, Andy. Thanks for sharing that. Yeah, I mean, I could say the same, but why don't I hop into oh, Craig says thanks too in the chat. You're welcome, Craig. I'll pop over to maybe some of the questions that we have. Let's see here. One of them was wondering, now that you guys have seen each other's submissions, is there anything that you were intrigued by or inspired by from viewing how other people approach this project? Did they do anything that surprised you, or did you see any places that you want to take like a little inspiration from? That's for anyone on the call. Go for it.
Well, I think as I gave Dimitri a bit of a call out, and it's like, yes, I saw some similarity there. It's very interesting of use of that. And you know, with this is one of our we also have a need for you know, the hydrogen engines at certain phases of flight, you know, if this works. So it's one of those things. And a blended wing, oh yeah, we need that for the area. So it was good to see somebody else was thinking about the blended wing aircraft, which also I think has which is coming to, well, I think there's a military project that's from I'd have to look it up, that's developing the blended wing, so it's getting closer to reality. So we're talking, you know, real blended wing possibilities in 2030.
Yeah, Jet Zero. I think Jet Zero
Yeah,
is working
yeah.
in the military. Yeah.
Speaking about me, I feel Jeff, yeah, looking at his idea, like his team idea, like this is what I thought, like when designing, like proposing a solution of two-stage aircraft. It could be like then second stage, the glider can be implement future technologies similar to space laser, and like the first stage booster will help it to take off, but then like it can fly, and like with support of space-based lasers or like any other sources like ground-based lasers, like taking like Jeff's team's idea.
Mm-hmm. Yeah.
That's
One
really
thing I thought
intriguing.
of, Dimitri, on your idea was, you know, using the liquid hydrogen in the first stage to get up and then separating for most flights, could you in fact utilize just gaseous hydrogen on the main craft? You know, because liquid is hard, gaseous is easier, and possibly, you know, looking at the system study, you know, what pressure, what tank size do we need there uh, to avoid the need to keep that cryogenic, you know, on the main vehicle.
Totally, yeah. I didn't mention it during my presentation today, but pressurized and liquid hydrogen but two solutions like to further investigate for some reason, like if we define like we split the system like perfectly, it can it can utilize pressurized hydrogen, like especially like the idea was to launch the aircraft with higher cruise altitude, and then we will exchange higher altitude into its range, flight range. So it would be a sort of trade-off, and therefore because of blended wing body properties, it can stay longer with less fuel consumption, and therefore like carry pressurized hydrogen instead of liquefied.
Mm-hmm. Nice.
I'm really inspired by the way you all took rather unexpected routes to solve this problem, and I want to ask about that in a moment. But particularly for yours, Dimitri, you weren't the only one to take this tact, but I think a lot of people questioned why, you know, does the aircraft need to necessarily stay in one piece or function in the exact same way as prior aircraft have done for the whole journey? Which reminded me of, I think there was a news article or a story I'd seen about how when they're trying to deliver medical supplies to remote communities in parts of Africa, they've invented a solution that sends smaller gliders to drop the supplies by like a parachute box, and the glider just returns and gets caught by a net. So it's really low tech, but it actually makes the response time for getting those supplies out there like 30 minutes to an hour, which is incredibly fast for the rugged terrain. And yeah, I guess I wanted to ask, again, for Alpha teams here, how did you begin your process of approaching this problem? Because the way we phrased it is there are many solutions that exist out there. There are lots of people who are trying to solve this. Andy talked about SAF. There are people who've already done a lot of things. How did you take this problem, get to the core part, which was reducing emissions, and decide this is my preferred pathway? What was that process like for each of you? Maybe we start with Dimitri.
You want to go
Oh,
first?
sorry.
I'll go if you want.
Go ahead, either way.
Okay, you know, we've done a number of these things, and now Google Chat is a home for much brainstorming. So we have a Google Chat that must be 50 pages of diagrams and links. I mean, we first started on this thing, I'm thinking, we always were thinking some sort of beamed power is what we were thinking. But the problem is, it's like, oh, geez, what are we going to do? It's like, oh, batteries. Oh, batteries are heavy. And beam power for this much energy, like microwave, if we were talking microwave, electric, or we're doing things on the ground, where then we're looking up, different, power things that the Army are doing and trying to gather numbers and say, geez, can this balance? Is there a way to balance this that makes it so an airplane can still fly? Because, we're thinking about using power to do electrolysis of water and split it and then reform as essentially a hydrogen engine on the back, right? Kind of like essentially be like a jet engine. So you can go very high and this and that, but the weight for the electrolysis, even if you beam that power, it was just too high. So we went through a whole bunch of things and we finally get down to, yeah, let's go with this, add this, add this. And and we were surprised that actually we found components with not unreasonable TRLs and some heritage that could come together for this. I know there's a couple tough ones, but I think that's kind of what we do. We do a lot of research and we do some calculations, and that's the way it works with us. And and this is what you get.
That's awesome. Thank you, Jeff. And then Craig, if you have a response too, feel free to put it in the chat. But yeah, I'll pass it to Dimitri now.
Speaking about me, so I started from the university presentations Andy provided, and then I watched the webinar called Cheetah. I'm sorry if I mispronounce it. And yeah, I looking at the solutions they provided, I saw how the complicated the system, like with all the fuel cells and how difficult it is to manage liquefied hydrogen, and like how it basically it requires like large tanks to carry hydrogen on board. I saw like the system gets very complicated and there are few existing technologies can just be implemented to make it work. And also personally, I'm interested in VTOL technology, and then I'm a spacecraft enthusiast, so that's why I came like to a multi-stage solution implements in VTOL and staging, and blended wing body is go-to solution for like large company concepts. So that's why I mixed things up and came to solution which would work in very many different situations.
That's fascinating. Thank you both. To Kevin's point that he added in the chat, it sounds like you each had kind of your own backstories or interests that informed how you started your solution seeking process. And then once you got there, it kind of revealed what were the problems you had to change and adapt to and identify. So that's really fascinating. Thank you all for sharing that. I think are about at time here. We've maybe got a few more minutes. So I will pass it over to yourself, Andy, one last time if there's anything you wanted to share, but then I will hand it over to our other panelists just to say their final words. However, it does look like Craig added it to the chat that a key part of his solution was that it would work with existing facilities, and that he was trying to find something that could be deployed cheaply, something that had some proof and high TRL level, like you guys had mentioned before. And so, as he called it, cheap in some ways. But yeah, thank you for adding that, Craig. I appreciate it. All right, Andy, any final thoughts?
Yeah, I mean, maybe you can see me looking through my notes here. I have a sister project called CAS, which is Convergent Aeronautics Solutions. And they try to come up with new ideas to solve problems. And they do have a project, an effort that they're just recently started on power beaming. So I was looking for the acronym for it and trying to find some information that probably wouldn't be ready online yet, but I will pass along more information on it to our power beaming team here. So once I find out a little more, have it in my notes somewhere. I just couldn't find it. That's really the only thing left. I think that's I have nothing else really to add. Again, congratulations. This was wonderful.
Well put, Craig. I appreciate it. I'll say the same. Congratulations to all of our panelists here and those who aren't on the call, and to everyone who participated. Thank you for your assistance in this important challenge. Last, Jeff, Prax, Dimitri, and Craig, I'm going to give you guys the final word. If there's one thing you wanted to tell our audience, Jeff, anything for you?
Oh, it was a fun project. We've done a number of HeroX. HeroX is good. We've done these on a few different platforms, including different ones for NASA. But HeroX has been a good platform. We've used that for years. So
Great.
Glad to hear that. Thank you. Anything to add, Prax?
Yeah, as I said, HeroX is a good platform for everyone who have the interest to solve the challenges and all. And thanks for this opportunity. And I would like to thank my team, the team Widget Blender. We have worked for late nights. I'm from Asia and they are from the America continent. So our time which is something will happen in between. So we adjusted our time and we done our brainstorming in between. So I really happy for that. And yeah. Thank you for this opportunity.
Wonderful. Thank you. Dimitri?
I really enjoyed this competition. I also participated in a few other NASA challenges. And speaking about this particular challenge, I found that it's more creative, the solution required to be rather creative than technical. And it was really fun to think about what could be the future of aviation, of zero emission aviation look like.
Okay.
Glad to hear that. And then Craig, I'm sorry you weren't able to get your microphone working, but thank you to you for joining us too. And Craig is also a repeat solver at HeroX.com, and so I want to thank him for all of his work. All right, that's it, gang. This will be posted onto the HeroX page in a few days once we get the recording edited. And then you can share it with anyone you'd like after that. But thank you again for participating and joining us, and have a great day, everybody.
okay, thank you.
Thank you, everyone.
Thanks, Shane. Thanks, everybody.
Thank you.